Hello, this is Jack Jackson, and we're going to be talking today about continuous distributions and using the CDF, the cumulative density function, to do some calculations. So this follows up my last video where I talked about how we go from a discrete case to a continuous case and how we see probability in both the probability density function, PDF, and the CDF. We saw that the PDF, the probability density function, was a curve that was above the x-axis. Usually it was at least piecewise continuous. And probabilities were then seen as areas between the PDF graph and the x-axis. The cumulative density function, CDF, gave us a continuous curve on or above the x-axis, basically increasing from 0 to 1, and that gave us cumulative probabilities to the left, were actually y values on that. And we saw that we could take different kinds of probabilities and illustrate those all as vertical distances on the CDF graph. Now, y values and vertical distances are actually much easier to estimate and to calculate than areas. So in this video, we will start our study of continuous distributions with learning how to use the graph or formula of a cumulative density function, a CDF, to compute probabilities and inverse probabilities. Now, in subsequent videos, we will see how to compute probabilities given the graph or formula of a PDF, but we'll start those with distributions that give areas which are nice shapes. Uniform distributions give us shapes where we're just basically computing areas of rectangles. And triangular distributions basically boil down to looking at areas of right triangles. So those are two types of shapes that are very easy to find areas of using formulas from, elementary school geometry. After we get a handle on how to work with PDFs then a little bit, using uniform and triangular distributions, then we'll have to move on to using some technology. So the videos after that will examine connections between the PDF and CDF. We'll actually see how to take the PDF formula and get a CDF graph and vice versa using technology, just TI-84 level calculator technology, and we'll use that technology to calculate probabilities, inverse probabilities, and distribution parameters, really whether we're given the PDF formula or the CDF formula. We'll see how to do that. But first, this video, we'll be again looking at the CDF. It's important that we look at the CDF first, number one, because it's easier to do, and number two, because ultimately, when we do the numerical calculations with the calculator, the CDF is the main one that we're going to be using. So, what are the characteristics of a CDF, a cumulative density function graph? Well, it's on or above the x-axis, so we basically don't need to look down on the graph where there's negative y's because there's none of the graph down there. It's either on the x-axis or above. In fact, it's always between really 0 and 1 inclusive. So we really only need to look on the y's between 0 and 1. It's continuous, no breaks, so hence calling it continuous distribution, you're really talking about the CDF, which is a continuous function. So it means there's no breaks in it. Okay? It's non-decreasing, so it's either level, horizontal, or increasing throughout. It never decreases on any part. So basically, it starts at 0 on the left and ends at 1 on the right. Now the domain is all real numbers, but we can ignore any part where the CDF has a value of 0, which would be on the far left, or the CDF has a value of 1, say on the far right. It's only the middle part that's really interesting. So again, it starts at 0 on the left and ends at 1 on the right. That could be on the x-axis on the left, or on the line y equals 1 on the right, or instead of actually being on those lines, it could approach them asymptotically. So it could have an asymptote of the x-axis, y equals 0 on the left, and or asymptote of y equals 1 on the far right. And as any graph that has these characteristics is a legitimate cumulative density function, CDF, for some distribution. So let's look at some examples. So the graph may be on the x-axis for values less than some value a, and on the line y equals 1 for some value greater than, say, some number b. In between, it must increase, or at least not decrease, from 0 to 1. So in this case, the formula would be in three pieces. Be a piecewise defined function. CDF of x would equal 0 for x is less than a. CDF of x would equal 1 for x is greater than b. And there would be some other formula for x is between a and b, inclusive. So in this case, we could just graph the part from x equals a to x equals b if we want and ignore the rest. But if we do have it, we will graph more than that. We'll see the horizontal line, part of a horizontal line out to the left at y equals 0, and part of a horizontal line out to the right at y equals 1. But the interesting part is really between a and b, and if we want, we could just ignore the rest. So we're going to look at some different examples. So here's an example. Notice that the graph is 0 out here for this red part to the left of 4, and to the right of, looks like 10 here. It's also 1, it's horizontal there, and it's 1 there. And in between it increases. This one's increasing in a linear way. And so this one's actually equal to 1 on the far right. Everywhere from 10 to the right it's equal to 1, and everywhere from the 4 to the left it's equal to 0, and in between it increases in a linear fashion. There are other ways it could increase in a concave up fashion. This one is 1 to the right of 9 and 0 to the left of 2, and it increases in a concave up way between 2 and 9, but it's still increasing from 1 to 2. Now the next one is going to increase, but it's concave down. Again, this one is 0 on the left and 1 on the right, 1 to the right of 12 and 0 to the left of 4, and in between we got it increasing from 0 to 1. This formula would be defined in three pieces. We would have y equals 0 on this piece, y equals 1 on this piece, and some other formula for this part in the middle. But in practice, we could just ignore all this stuff to the left of 4 and to the right of 12, because we kind of know what it looks like. It's sort of obvious. The interesting part is between 4 and 12, and we could basically just think of our function essentially being defined on that interval, and we would get basically the same result. Then it would basically, if we graph this in a window where 4, 0 is at this end and 12, 1 was at this end, it would go corner to corner, increasing, concave down in this case. Now the next one's got some concave down and then some concave up. It could increase any way we want, but it can't, this actually is increasing the whole time. It cannot come back down. So it actually, this one has an inflection point in the middle, but it's still increasing and then level on the ends. Now instead of having a horizontal line at the ends of the graph, the CDF may approach a horizontal asymptote of y equals 0, that is the x-axis on the left, and or approach a horizontal asymptote of y equals 1 on the right. So we'll give a couple of examples of this, something that has an asymptote of 1 or both ends. Here's one that has an asymptote on the right. So essentially this graph might as well just be defined from 0 to infinity, because less than 0, all the y values are 0 on both the CDF and the PDF. So it's 0 for negative x. And then for positive x's, we get it increases the whole way. Now this one actually never actually reaches 1. It has an asymptote of 1. And that is okay for a continuous CDF. It doesn't actually have to reach 1, but it still is essentially increasing from 0 to 1. It just doesn't actually quite hit that 1 there. Of course, in practical purposes, at some point it's so close to 1 you can hardly tell the difference. So if you have this thing graphed right, you should basically see it level off to 1. Either it is 1 or has an asymptote of 1 on the right, and it should be 0 or approaching 0 on the left. Next we'll look at one that has an asymptote on both ends. Okay, and this example here, we see that y equals 0, or the x-axis, is our asymptote on the left. Y equals 1 is an asymptote on the right. So, for example, one of the most important distributions that we will look at, in fact, the most important distribution we'll look at, is called a normal distribution. And a normal distribution would look something like this for the CDF. Okay, let's go on. Now, how are we going to use this thing? Now we know what some of the shapes of the graph look like. How can we use it to do some computations? Well, first of all, recall that the y value on the CDF graph is actually the cumulative probability, that is a probability to the left of the input x value. So CDF of A is the probability that x is less than or equal to A, but that's also the same as the probability of x is less than A. In the previous video, we talked about this idea that the probability of x equals A is 0. So whether you include the A or not on the endpoint, it's irrelevant. So probability of x less than A or probability of x less than or equal to A are the same thing, and they are the output value, the y value on the CDF graph, CDF of A. So if we're given a graph of a CDF and an input value at x equals A, we can simply find the corresponding y value on the CDF curve to get the probability that goes with that. That is the left probability, the probability that x is less than or equal to A. And similarly, if we go backwards from that, if we're given the cumulative probability, if we're given the probability that x is less than or equal to A, and of course the CDF graph, we find the y value that goes with that x value of A, and that we find that y value that is P, that probability that's given, we find the corresponding x value, and that's A. That's the A that maybe is unknown. We call this probability type of question an inverse probability question, because this time we're given the probability and we want to find the value of x. Okay, we're given notice that what we're given here is a cumulative probability or a left-tailed probability. Now, so we can use a given CDF graph, a given x values, and a few facts to compute several kinds of probabilities just using y values, output to the CDF, and performing a few simple calculations. So if you want to find the probability to the left, probability of x less than A or probability of x less than or equal to A, all you have to do is just find the y value that goes with A, that's the CDF of A, and you found the probability that you're looking for. On the other hand, if you want to find the probability that x is greater than A, which is the same as the probability x greater than or equal to A, then you have to do 1 minus the CDF of A. So basically what you do is you find the y value that goes with A and then subtract that from 1. If you want to find the probability that x is between A and B, and again it doesn't matter whether you include A or B or not, that turns out to be CDF of B minus CDF of A. So in other words, you find the y value that goes with x is B, and you find the y value where x is A, and just subtract those two things. Now if you want to go backwards from that, we can do an inverse probability. So similarly, we can use the graph of the CDF to look up some x values for given y values to compute inverse probabilities, and you're basically using the same relationships above. So for example, if you want to find, if you're given the cumulative probability, probability x is less than or equal to A, you just simply take that y value, look up the corresponding x value, that will be A. If you want to find the, let's say we're given the probability to the right, probability of x greater than A, well remember that 1 minus the probability of x greater than A is going to be our CDF of A. So basically take this second equation right here, solve it. You got 1 minus CDF of A is probability of x greater than A. So let's see, add the opposite of this to both sides, subtract it from both sides, and then add CDF of A. We just solve that equation around the other way, and we see that CDF of A, which is a y value, is going to be 1 minus the probability of x greater than A. So if we're trying to find if we're given the probability of x greater than A, let's say is 0.6, then we do 1 minus 0.6 is 0.4, and we know the probability less than A is 0.4, and that's going to be our y value on our CDF. Look up the corresponding x value that goes with that, and you will find the A you're looking for. And you can do some similar things here. Now, using these techniques, we can solve several different kinds of probability and inverse probability problems. And we're going to, for the next several slides, we're going to look at a particular graph of a CDF. And let's see if you can put these things into work in the next next slides. So here we have a graph of a CDF. First of all, let's see if it's a legitimate CDF. The y values have to be on or above the x-axis. That's right. It has to be strictly increasing, or maybe non-decreasing at least. And it is strictly increasing, looks like. And what else? It has to be continuous, no breaks, that's true. And it has to be 0 on the left and 1 on the right. Looks like this one actually has asymptotes maybe on the left and right, but that's okay as long as they are 0 on the left, 1 on the right. So given this graph, and you've got a grid here, see if you can find these probabilities and inverse probabilities. So notice that the first three, I'm asking you to find probabilities. These last ones, I'm asking you to find x values given some probabilities. So the first one, we want to find the probability that x is less than 8. Then we want to find the probability that x is greater than or equal to 4. The probability that x is between 2 and 10. We're given that the probability is greater than 0.65 in this part, and we want to find the probability that x is less than a is 0.65. We want to find the a value. And this next one, we're given that the probability of x is greater than a is 0.8. We want to find a. And we want to find the median of the distribution in the 95th percentile. So really, I think given the stuff that we've gone over so far, you should be able to go ahead and figure these out. So here's what I'd like you to do. I'd like you to leave this screen up, press pause, and see if you can use the grid to work out answers for all of these questions. When you get them all worked out, then come back to the video. We'll go through them one at a time. Now, if everything's going fine, we'll do it. Just keep watching the video. But if after watching one you say, oh, wait a minute, I think maybe I didn't quite do that right, then stop the video again before you go on to the next one. Okay? But let's go through these 7 problems here. Okay? You work them first. Come back when you're done. Press pause now. Okay, now you're back. Hopefully that means that you've worked through these and we can take a look and check your answers. Okay, this is the same graph, slightly different view, but it's the same graph. And we want the probability that x is less than 8. That is, we want to find the CDF at 8. We want to find the y value when the x value is 8. So just find 8 here on the x-axis, go straight up, find the point on the graph, go across here and find the y value, and you should have seen it should have been around 0.8. In fact, it's exactly 0.8. By the way, the probability that x is greater than 8 would be then 0.1 minus that 0.8 would be 0.2. And you can see both of those as vertical distances here. This purple distance from here up to this value, or the same as this purple length here, that is the probability of 0.8. The horizontal distance across here is just the x value, and the orange distance here is the complementary probability of 0.2. So the probability that we get an x to the left of here is this purple distance, 0.8. Probability we get an x to the right of here is this orange distance, 0.2. Okay? Okay? Now, if you haven't done it already, the next problem is find the probability that x is greater than or equal to 4. Pause the video again if you haven't done that one. But if so, let's check it. Alright, so we want the probability x is greater than or equal to 4. Well, remember the CDF deals with probabilities to the left, not to the right. It deals with less than probabilities. So the probability that x is greater than 4 is 1 minus the probability that x is less than 4. That's 1 minus the CDF of 4. So we find 4 here. We go up. We find the y value, which turned out to be 0.45. Then we have to subtract that from 1 to get 0.55. We can see the value we're looking for is this orange distance. The purple distance from here to here is the probability that x is to the left of this value, which is the same as just this y-coordinate right here, or here on the graph, above x is 4. And that is 0.45. The remaining probability to get you up to 1 is 1 minus that, which is 0.55. So the probability we're looking for is 0.55. Okay, the next one we want to find the probability x is between 2 and 10. Okay, see if you can figure that one out before you go on. The probability that x is between 2 and 10. Well, the way we can do that is CDF of 10 minus CDF of 2. In other words, it's the probability that x is less than 10 minus the probability that x is less than 2. So that's CDF of 10 minus CDF of 2. In other words, the y value when x is 10 minus the y value when x is 2. So find 10 on the x, come up here, find the y value there, which looks like 0.9, find the 2 on here, go up, find the y value here, which looks like 0.27, subtract, you get 0.63, and we can see that is this green length here, which is a vertical length between the two y values here and here, which are the y values of this point above 2 and the y value of this one above 10. And so the vertical distance between these 2 points, that is this green distance, is the probability that x is between 2 and 10. So that green line segment from here to here has length 0.63, and that is a probability. So notice we can see probabilities as vertical lengths on the graph. And so we've just seen how to take to do a less than probability, a greater than probability, or probability x is between two numbers just by reading them straight off of the graph if we're given the graph of the CDF. Alright, now the next problem is backwards. Okay, it's an inverse probability. Okay, so we will have we're given the probability that x is less than a is 0.65. Well, that's the CDF of a. So we're given that the CDF of a, that is y, is 0.65. We want to find the corresponding x. So this time we find the 0.65 on the y-axis, go across to the graph, and then come down and see what that x is. And you should have gotten about 6. To a couple decimal places, it's actually 6.03. But if you came up with 6, that was pretty good based on what you saw in this graph. So again, if we're given a probability to the left, that's a y value on this. We can, given a y value, we can read off the course. We can find the point where that y equals that. So you basically take a horizontal line at y equals 0.65, find where that crosses the graph, bring it down vertically, and find where that crosses the x-axis. That'll give you the x-coordinate at that point when you know the y. Alright, here's another one. This time we know the probability to the right, not to the left, a greater than probability. Well, if the probability that x is greater than a is 0.8, the probability that x is less than a is 1 minus the probability that x is greater than a, which is 1 minus 0.8, which is 0.2. And remember, that is the CDF. So the y value we're looking for is 0.2, not 0.8, but the complementary probability of 0.2. So we find the y value is 0.2 here, go across, find this, and here's the x value, so which was about 1.01. So if x is to the left of this 1.01, we see a probability of 20%, and to the right of that we see a probability of 80%. So when we were doing a right probability, we had to do a little bit of adjustment to find what the left probability was first. Then we could use the graph, because remember, this graph is only about left probabilities, cumulative probabilities, probabilities of x less than the number. Now, let's see. What about the median? Well, the median of a distribution, if you remember when we were looking at discrete distributions or just data in general, the median was a value so that, an x value, so that half of the data was below it. So this is also known as the 50th percentile, okay, or the second quartile. It is a place where it's an x value so that 50% or 1/2 of the probability is below it. So the cumulative probability is a half. So this is an inverse probability problem. What we're looking for is a y value here of 0.5, which is right here, and we just come across and find the corresponding x value right there and bring it down and find out what the x is that goes with that, and it turns out to be 4.48. So the median is 4.48. What does that mean? That means half the probability is below it. Of course, if half the probability is below it, then the other half of the probability is above it. And so notice the probabilities are vertical distances here. So you're right at 0.5 here. So it's a distance of 0.5 down to 0, and it's a distance of 0.5 right up to 1. So it cuts it exactly in half in terms of the probability. Half is below, half is above. So the y value is exactly halfway between 0 and 1 at 0.5. The next one, we want to find the 95th percentile. See if you can do that one before you flip to the keep the video going, so you could pause if you need to. Okay, you're back, so I assume you've done that. So what do? Again, we know the 95th percentile is an x value with the cumulative probability of 5% or 0.95. So there's 0.95 is the probability to the left. So that means you just go up a vertical length of 0.95. In other words, we find 0.95 as the y value. Pull that straight across horizontally, find that x value that goes with it, and that x value right there is the 95th percentile, which in this case it looks like it's about 11.85. Okay, you might not have been able to get that many decimal places by just looking at the graph, but you should be able to get pretty close. Probably could have gotten about 11.9, 11.8, somewhere in there. You should have been able to estimate pretty closely from looking at the graph. So what we've seen in these examples is that if we are given the graph of a CDF, we can find probabilities and inverse probabilities by just reading off xy coordinates on the graph. Basically, if we're given an x coordinate, we can find a y, and given a y, we can find an x. And since we know what these x and y coordinates stand for, we can find out probability problems and inverse probability problems of various types. And we've seen examples of that. Now, what if we're given a formula rather than a graph? Well, first of all, if we're given a formula, we can make a graph if we have a calculator, graphing calculator. So, for example, if you've got a TI-84 calculator, you could let y1 be the CDF formula, and then we can use the graph to help us compute probabilities and inverse probabilities, or the built-in formula. So let's try that. So get out your calculator. Okay, whatever kind of calculator you're using. I'm assuming that you have some kind of graphing calculator for this. So the CDF formula we're going to look at is 1 over 1 plus 2 times e to the negative 0.3x. Now, when you're putting this in your calculator, remember you have to understand the structure of this function to get it in your calculator, because a horizontal line is a grouping symbol, as is this superscript here. So the superscript says all of that is one thing, which is the exponent of the e, and we do the entire bottom and top separately and then divide. So we need parentheses here when we're putting it in our calculator. Okay, you need parentheses around the entire denominator. You should put around the numerator normally, but since it's just a single number, that's optional. But you also need parentheses around the entire exponent here as well. So you're going to have 1 divided by parentheses 1 plus 2 e to the negative 2 e to the power parentheses negative, not subtract, 0.3x, close parentheses there for the power, close parentheses for the denominator. Now get that in y1 in your calculator, say if you have a TI-84, or do the equivalent on whatever calculator you have, and then see if you can figure out how to find these probabilities and inverse probabilities. The first three are probability problems. Compute the probability that x is less than 5, the probability that x is greater than 7, the probability that x is between 4 and 8. Compute those three probabilities. Of course, they're probabilities, so you know you should be getting something between 0 and 1. Next, find some inverse probabilities. If we're given the probability that x is less than a is 0.4, find the a. We're given the probability that x is greater than b is 0.05, find the b. And then also find the median. So there are 6 problems, 3 probability problems, 3 inverse probability problems. And see if you can go ahead and work these out on your own, using your calculator, and then come back and we'll check your results. Okay? press pause now. Well, looks like you're back, so let's take a look at these to check your answer. Alright, here's the first one. Okay, the first thing is we got to get this in our calculator. So as I mentioned, watch your parentheses. 1 over 1 plus 2 e to the negative 0.3x is 1 divided by parentheses 1 plus 2 e to the power of parentheses negative 0.3x close parentheses close parentheses. So that's y1. And we need to decide on some window. Now, the window is basically always the same for y. Basically, you can just take y going from 0 to 1 because the y values, well, that's exactly what they will do. They'll run from 0 to 1. Now, I kind of like mine to show a little space above and below that, so I usually run my window up to 1.1 so that this isn't running right across the top of the screen but just below it at a horizontal line. And I go down to negative 0.2, and that leaves me some space because when the calculator does calculations, it displays those down here, and that will keep them off of your graph, perhaps. So I always use this y window, y settings on my window. Y min is negative 0.2, y max is 1.1, and a y scale of 0.1, and that works nicely for a CDF graph no matter what. Now the x min and x max and the x scale, that's a little harder. That requires you to maybe do a little trial and error. But what do we know? We know that we should see basically a horizontal looking piece on the left and a horizontal piece looking on the right. And of course this should be at 0 on the left and 1 on the right. If you don't see it leveling out, you need to expand your window out to the right and to the left. If you see it going nearly vertical in between and mostly all to horizontal here and down here, you probably could zoom in a little bit on the left and right here, come in a little larger x min, a little smaller x max. But it does take a little bit of trial and error perhaps. You can look at your table, that might be helpful. But using, maybe looking at your table, using a little trial and error, you can decide on an appropriate window for the x min and x max, but leave your y min and y max, what I have here, all the time, anytime you're working with a CDF. Now we have this, and what do we know? We want to find the probability that x is less than or equal to 5. That is just CDF of 5. So we just want to find the y value, and so we can look at our graph. Now how can we get our y value from a graph if we know the x value? Well, it's pretty easy. On a TI-84, for example, so we can just enter trace. Now remember, trace is second calc. Trace is just trace is just a button on the calculator, and you can see it here. It's right up here, trace. Okay, so this is not the right graph up here, but if I just hit trace, I can enter in an x value, like trace 5, and it will go to that. It's outside my window here. Oops. I have to give it something that's in the window. Trace, I'm not sure where I am. Let's say trace 4, and it gives me a point there. It gives me the x and y. So I can do that with a trace. That's not this particular graph, but another one. So if you put this graph in there and hit trace, you can just type in the value you want, 5. It'll go to that point. It'll tell you the y value, which is our cumulative probability, which is what we're looking for. That is this y is the CDF of 5, which is this cumulative probability. Now, your calculator also knows function notation, and so we can do y1 of that and work out what we want here. Let me pull this calculator up. And look at this again. Okay, so let me actually get the right formula in here and a decent window. So 1 divided by parentheses 1 plus e to the power negative 0.3x, close the power, close the denominator, and what do we say a window would work for us? Negative 20 to 25 seems to work okay. Actually, I'm going to, yeah, you can leave it marked off in ones, is fine. And then there's my standard window for the settings for y. We graph it, and this should look, this picture should match this one right here. Okay, good. So now I can just do trace and 5 and get it. I could also do a table. If I do my table, as long as my table has 5 in it, so let's say maybe start at 1 and go up by ones, I should get 5 in my table, and there's the y there. So it's another way to get it. Or another way we can do it from the home screen, and this is kind of useful, is to just do this, is to say y1 of 5. So if you hit variables, then go to y variables, choose number 1, which is function, then there's y1. Okay, let's go over that again. Variables, it's written down, it's not there, I've written it down another place somewhere, but it's variables, then right arrow to y variables, choose number 1, which is function, and then number 1 is y1, and then you just put in the argument, which is 5. So it's CDF of 5, y1 of 5, and that gives you your value there, 0.69143854. Of course, at some point you'll probably round off in real-world problems, but that's the to that many digits, that is the accurate probability if this was exactly 5 that we're plugging in. So you can get it from the home screen, or you can see it visually on the graph as well. Okay, so let's go back to our slideshow here. Alright, so continuing on, let's do our next problem. So next we wanted to find the probability that x is greater than 7. If you haven't worked that one out, see if you can, now that you've seen this example, see if you can do that one. Well, we continue on. Notice it's the same formula, so I don't have to change what's in y1. It's the same thing there. But notice that the probability that x is greater than 7 is 1 minus the probability that x is, x is less than 7. So it's 1 minus the CDF of 7. So that's 1 minus y1 of 7. So from the home screen there, I just type in 1 minus y1 of 7. Once again, if you want to look at the calculator here, we just type that in, 1 minus. Now, let's go over again. It's variables, to y variables, function, y1 of 7. And since I have the CDF formula put in y1, this will give me the probability. The y1 of 7 gives me the probability that x is less than 7, and 1 minus that is the probability that x is greater than 7. Now here's a shorter way to get to y1 if you have the newer operating system. So 1 minus, and to get to y1, it's F4, which is alpha trace. And then you can get all your y1, y2, whatever from there. So you can type it in a little bit faster that way if you have the newer operating system. Okay, back to the slideshow. Okay, so there it tells you y variables, right arrow to get to y function, y1. You can see that on the newer TI-84 alpha trace gives you F4, which gives you to y1 that way. Okay, let's see if you can do the next problem. The next problem is we want to find the probability that x is between 4 and 8. Well, how do we do that? Well, remember, the probability that x is between 4 and 8 is just CDF of 8 minus CDF of the 4. CDF on the right end minus CDF on the left end. Well, that's just y1 of 8 minus y1 of 4. That's our same y1 in there. And of course, there's what we come up with. So a little over 22%. Okay, now how are we going to do an inverse probability? Okay, before I show you the answer to this one, let's think about this a little bit on the next question. So the next question is, we're given the probability that x is less than a is 0.4. So the probability we know is 0.4. How can we get the calculator to tell us the corresponding x value that goes with that? Now what we're saying is that the CDF of x is 0.4. Okay, so the CDF is 0.4. That's a y value on the CDF graph, and we want to find the corresponding x. How do you find an x value given a y value on the TI-84? We can use trace, or we can use y1 here if we know the x and we want to find the y. But what about backwards? How do we do that backwards? Let's take a look at that. Well, anytime you have a graph, any kind of graph, and you want to know the x given the y, what you can do is, here in y1, we have our formula for our CDF graph, and y2 is our cumulative probability. It's a probability to the left. Now remember, CDF is always a probability to the left, a less than probability. So the probability to the left is 0.4, and when I graph y2, I get a horizontal line, see? And what am I looking for? I'm looking for the x value where they cross. All you have to do is calculate the intersection. On our calculator, second trace is calc, and then you go down to number 5 here, or just second trace, and hit the 5 button. Will be calculate the intersection. Now when you're calculating this intersection, well, let me take you through it here on the calculator. Okay, so we go to here, we put our cumulative probability here, which this case was 0.4, was it? Yeah, 0.4, so that's got to get down to y2. Okay, let's go ahead and graph that. So it's going to graph the CDF first, then it's going to graph y equals 0.4. We want to find where those two cross each other. So calc is second trace. So second, and then the trace button will be calc, and it's number 5 intersect. So I'm just going to hit the 5 button. Now when you do a calc intersect, you have to identify which two curves. Now if you only have two curves up here, it's real easy. Just hit enter and enter again. But you know, you could have as many as 10 different graphs going at once on a TI-84. So you identify that curve by hitting enter, and then you go to the other curve and then hit enter, and then you arrow over to close to where they cross, and then they enter that for your guess by hitting enter one more time, and then it will go to that point of intersection and tell you the x and the y. Of course, we know the y is 0.4. That's the cumulative probability. What we didn't know starting out was the x value, and there it is. So this screen is the same as the last screen here. That's how you do calculate an intersection. And that's how you find a cumulative, that's how you do an inverse probability problem. You put the cumulative probability as y2, y1 is your CDF, calculate the intersection, boom, you've got the x value you need. Okay, so let's do the next one. If you didn't get this already, now that you've seen that example, see if you can do this next one. Probability that x is greater than b is 0.05. So the probability to the right is 0.05, 5% to the right. What's the x value? What's the b value? Okay? If you haven't done that one, press pause and do it yourself now and come back and check it. Okay, so let's check it now. So if there's 5% or 0.05 to the right, then the probability that x is less than that b is 1 minus the probability that x is greater than b. It's 1 minus 0.05, which is 0.95. So if 5% is to the right, or 5% is above this, then 95% is below it. So you want to think of, so if we go an x to the right of this, we're talking about a probability up here between this horizontal line and 1, which is small, only 5%, but 95% is the distance below that, and that'll be the probability that goes from this x all the way across. The x is the x we're looking for, is our value of b. So let y1 be the CDF formula as always, and y2 is the cumulative probability that is a left probability, 0.95, 95%, 0.95. Again, calculate an intersection and enter that in, and we get our x value that we're looking for. Of course, our cumulative probability is 0.95. That's the left probability again, leaving 5% to the right. The x value that we're looking for is 12.125287. Okay, so the next problem is we want to find the median. What do you know about the median? Well, you know the median is a probability of 0.5 for the cumulative probability. So we know the probability to the left of the median is 0.5, so it's the same kind of problem. It's an inverse probability problem. You let y2 be 0.5, see where that horizontal line crosses our CDF graph by doing a calc intersect. And this x value here, 2.3104906, that is at least to that many digits in our calculator, which is more than we're likely to need in any practical situation. That is going to be the x value for our median. Of course, the median is an x value. It's a value with half to the left. Also known as the 50th percentile, because 50% is to the left. So what if we were going to try to find the Q3? How would we find Q3? Well, we put in 0.75 here instead of 0.5, and the line would be drawn up here. Find where that crosses, and that would give us Q3. Or if we want Q2, that would be 0.25 here, and down here somewhere it would cross. Or if we, so that would tell us our quartiles. What would we have if we wanted to do the 80th percentile? Then you do 0.8 here. So we can do any kind of percentile or quartiles problems like this. Now, there is a special case of a type of inverse probability that we sometimes like to find too, but it's a very special situation where we have a symmetric distribution. Now, symmetric distribution means that the PDF graph is symmetric about the mean, and the CDF graph will have point symmetry about the point mean, comma, 0.5, and the mean and median will both be the same thing in a symmetric distribution. So if we have a symmetric distribution, we can find a special kind of inverse probability centered on the mean. So remember, the mean is mu, so we want to find the mean minus some number k up to the mean, that should say plus that number k. That should be a plus right there as a typo. Okay, so from mean minus k up to mean plus k, we want to find the x's between that. Well, so that would be, if that's the probability we're looking for, notice that what's left, what's outside of that, the part that's to the left of mu minus k, plus the part that's to the right of mu minus k, has to be 1 minus whatever this probability here is. So if we call that probability p, 1 minus p has to be the sum of these two probabilities. Now that's true in general, but because it's symmetric, these two probabilities are the same. To the left of mu minus k and to the right of mu plus k are the same, so these two probabilities are the same, so they're just twice the probability of x being less than mu minus k. So the probability that x is less than mu minus k is 1/2 of 1 minus p. Well, this probability right here is a probability to the left. That's a CDF. So we're saying that the CDF of mu minus k is 1 minus p over 2. And that's going to allow us to solve this problem. Let's take a look at what one of these graphs would look like. So here's a graph here. I've graphed both the CDF and the PDF. So the CDF looks like this, and the PDF is this kind of a bell-shaped curve here. So the PDF is in blue down here, this kind of bell-shaped thing, and this kind of elongated S-looking thing is the CDF in red. Here's the actual formula for it, for the CDF. Okay? Now, this is similar to, but not the same as, a normal distribution, which is probably the most important distribution that we might look at. This is not a normal, but it's got some similar characteristics to it. So what we see here is this particular one is centered up at 0. So the mean and median are both 0. So the PDF here is symmetric about the y-axis. This half of the graph is a mirror image of this half of the graph. So the first and second quadrants are mirror images of each other. Now if you take that same x value and come up here and find this point right here, now on the CDF graph, notice it's at 0.5 for the y value, so it's the median, but it's also the mean. It would be a balance point on this area for the PDF graph. And if you take the CDF graph and we spun this thing upside down, rotate 180 degrees, this part here to the right of that 0, we'd spin it with this being the center point of our spin, then this part would spin around and be on top of this part, and vice versa, this part would spin around and be on top of this. So it has 180 degree rotational symmetry about that point right there, which is the mean, comma, 0.5. And so this is what happens when you have a symmetric distribution. You have some point symmetry on the CDF graph, and you have some line symmetry on the PDF graph. Okay, so how can we do a problem here? So here's a problem we might want to find, and here's the solution to it. Again, here's the same graph we were just looking at. Here you can see both the CDF and PDF here. So we want to find both the lower and the upper limits here, which are centered on this. That should say mu plus k. It's the same typo again. That's irritating. Let me get out of here and fix that. So that should be a plus, and let's back up 2 slides, and it was that same problem there. This one should be a plus. When you do cut and paste, you make a mistake once, and then you end up making it twice. Okay, but we're on this slide here. Okay, now we're back. Okay, so this is, the L value is mu minus k. That's this value right here of L, x value. And this value here, U, is this value, which is mu plus k. So this distance, mu is 0 in this case. So this distance from here to here is the same as the distance from here to here. Since it's centered at 0, these actual U and L will actually just be opposite signs of each other. If we were centered somewhere else, they would not necessarily be opposite signs. So if we want to find the probability that x is between this lower and upper, we're given that that's 0.8. Now again, this only is going to work for a symmetric distribution. Okay? And only then if we're centering it up on the mu. So mu is right in the middle of our interval from L to U. Okay? Well, we know that the probability that we're between L and U, this area right in here, or the vertical distance from here to here, this orange distance, that has to be 0.8. So that leaves 0.2 for the stuff that's outside, the area to the right of this and to the left of this put together in that graph, or that length here, this vertical length here, the unshaded part here, plus the vertical length here has to add up to 0.2. But because it's symmetric, these two parts are evenly split. So it's 0.2 evenly split into 0.1 down here. That is the area to the left here under the PDF, or the probability to the left of L is 0.1, and then 0.1 also for this part up here, this distance is 0.1, or this area down here is 0.1, that is the probability to the right of U is 0.1. So, which one do we want to use? Well, we know areas to the left, or probabilities to the left, areas under the PDF, this vertical distance on the CDF, that has to be 0.1. So that's a CDF. So we know the probability that x is less than L is 0.1. So what do? We just put our formula in for y1. For y2 we put 0.1. We calculate that intersection, and we get negative 3.1, well, about 3.14 actually. Let's correct that. So about 3.14, that should say. and u is positive 3.14. Because of the symmetry, we know that it's the same distance here. So we could actually figure out this distance and add it to 0. Or we could do the same kind of thing to find the upper one. If there's 10% above the upper one, there's 90% below it. So I could put 0.9 in here, draw a line up here, do a calc intersect, and that value would be the upper that we're looking for. So that's a very special kind of situation. Okay, one more topic that we want to look at. Suppose we have a graph that doesn't have asymptotes on the end for the CDF, but it's rather a piecewise defined function. How can we get that in our calculator, say in a TI-84? Well, it's actually possible to do that, and let me show you how this works. So this could be the formula for a legitimate CDF. It's 0 for x is less than 2, it's 1 for x is greater than 4, and for x is between 2 and 4 inclusive, we have the formula CDF of x, or y, equals 1/4 times x minus 2 squared. If we graph that, we should get a graph that looks like this in the middle. But how do you get a graph like that on your calculator when this is in pieces? Well, here's how you do it. You put the first formula 0 in parentheses, and then you put this condition here next, x minus 2 in parentheses. Then you put plus. We put the middle formula 1/4 times x minus 2 squared in parentheses, and we put this condition here, which is actually two conditions. 2 is less than or equal to x, and then also x is less than or equal to 4. Plus, we put this formula right here in parentheses, and the last condition, x greater than 4. All right, wow, that's kind of complicated. What does that tell us? Well, first of all, how do we get it in there? How do you get the less thans and greater thans and less than or equal to's and all that? Well, if you do second math on the TI-84, that's test, and you'll find them there in a list. And so you can get those. Now, how does this work? Well, if you just take the x less than 2 and you put in a particular x value as it's trying to evaluate this thing, whether it's doing a table or a graph, then this is a statement which is either true or false. If it's true, it'll return a value of 1, and if it's false, it'll return a value of 0. And that turns out to make this thing do exactly what you want. So, for example, if x is less than 2, this x greater than 4 will return a value of 0. So 0 times 1 is 0, so we're adding 0. So that part just goes away. And this x less than or equal to 4, let's see, if an x is less than 2, this part here, 2 less than or equal to x would be false, so that would return 0, and the middle part would go away. But the x less than 2 would be true, that would return a 1, we get 1 times 0, so we get 0 plus 0 plus 0, we get a 0, and that's what we're supposed to get. If the x is bigger than 4, this part will be true, so it'll return a 1. This will be true, it'll return a 1, but this will be false, so that'll return a 0. Then this part is 0, this will be false, so that's a 0. So we get 0 plus 0 plus 1 is 1. If x is between 2 and 4 are inclusive, this will be 0. The x less than 2 will be false, so this is 0, so that goes away. X greater than 4 will be false, so this will be 0 for that part. This part will be 1, and this part will be 1, and so what you're left with is 1/4 times whatever x is minus 2 squared, and it gives you the right thing. Now, granted, that's kind of complicated, okay? But that's what you have to do to actually get the full graph. And then if you graph it, I've made it kind of thick here so you can see it. You actually do get 0 here up to 2. Then you follow this part of a parabola here, quadratic graph from 2 to 4. And then it's 1 from 4 on. If you look at your table, for things bigger than 4, you get 1. Things less than 2, you get 0. And in between, it follows this formula here. It does exactly what you want. Here's the window I was using. So that's one way you can do this, and then of course you can use this for the CDF. However, you really don't need to go to this much trouble. This part here is really irrelevant, and this part over here is irrelevant. You might as well just think of this function as only being defined between 0 and 4, and know that if you actually want to put in something bigger than 4, you know the cumulative probability is 1. You don't need to look at a graph for that. And if you're talking about some x value less than 2, well, you know the probability is 0. You don't even need to look there. The interesting stuff is between 2 and 4. So in fact, the easier method is just this. Just graph the middle part. let y1 be the 1/4 times x minus 2 squared. But here's where you have to be careful. You have to be careful that you only graph from 2 to 4, because the way this is set up, it doesn't level off at 1 here off screen. It's actually going up when the real graph just levels off at 1 off screen. And this actually turns around and comes back up this way, or it's coming down on this side here for this formula. But that's not our PDF or CDF there. It's actually 0 for a CDF. So if you only look between 2 and 4, this is correct. And if you only graph that, in fact, if you had your window set from 0 to 1 on y, it would actually go corner to corner. But y values are going from 0 to 1 here. And this works just fine. The only thing you have to do is just only look between 2 and 4. But you can graph this, you can find probabilities, inverse probabilities, and so forth. Just make sure you're only dealing with x's between 2 and 4. Everything works out just fine. So there's really no need to go over here to this this piecewise defined stuff, unless you just really want to see the whole graph and see what it looks like. If you do, you can do this, but it's probably a little bit more trouble than it's worth. Just stay with this method, and it'll be a little bit easier. So we have seen how to take a continuous distribution. If we're given a graph, we can find probabilities and inverse probabilities. If we're given a formula for the CDF, we've seen how we can use our calculator to find probabilities and inverse probabilities of various different types. In our next video, we'll start looking at how we can take a PDF graph and see probabilities on the PDF graph.